Welcome. This is my second video on composition of functions. If you've not watched the first one, I recommend you do that first, where I go over the basic definition of composition of functions and a few symbolic examples. And then in this video, we'll look at a few of the other things we can do with composition of functions. So we'll pick up here with examples 5 and 6. So composition of functions, it's a process where you take one function, substitute it into another to get a new function. Once you do that, you've created a new function, which could then be used for composition of functions. So it's a process that can be repeated over and over. You can do it with any number of functions. I'm going to just go up to 3 here. We did 2 with functions in the previous video, and here I have 3 functions that we're going to do composition. I have f of x is x plus 2, g of x is x squared, and h of x is 1 over x. And we're going to find f of g of x, h of g of f. So the first thing I'm going to do is write that in nested notation. This is the order here. We have to work from the inside out by function notation. We need to do h of g of f of x. So I'm going to go from the inside out. F of x is x plus 2. So if I substitute that in for the function notation f of x, we need to do h of g of x plus 2. Well, g of x plus 2, I would take g's formula x squared and plug in x plus 2. So I would get x plus 2 squared when I substitute x plus 2 in for the x into x squared. And now I have one more step to go. I need to do h of x plus 2 squared. Well, h is just 1 over x, or 1 over the input, so I remove the input and plug in x plus 2 squared, and there's my result. I get 1 over x plus 2 squared. So in this order, I begin with f, substitute that into g, take that result, substitute that into h. I'll point out you could multiply out x plus 2 squared. You could FOIL that out to get x squared plus 4x plus 4. You would have to FOIL it and get the middle term. But it's actually probably preferable with the fraction to leave it in this form, because I can see for my domain I can't plug in -2, so it would actually be easier to tell the domain of that function in this factored form. So either way would be fine. Another thing we can do that becomes useful in more advanced math classes is to go in the opposite order, decomposition of functions, to be able to look at a function and recognize it as the result of putting 2 simpler functions together. Okay? And what I like to say here is you're pretty much literally looking for an inside and an outside function. Okay? And that outside function could be things like absolute value, square root, power functions, trig functions, logarithms, any of the type of functions that we encounter in algebra. I did say don't use x for either function. If you look at it and you think about it, if you let one of the functions be what I've given as h of x and the other function be x, when you do composition in either order, you just get the absolute value of 2x minus 3. That's what we would call the trivial solutions. But what I'm really asking here is for you to decompose h, find an inside function g and an outside function f, that if we did f of g, we would have this result. Okay? So we're trying to find g and f so that f of g of x would be absolute value of 2x minus 3. Again, look for an inside and an outside. There is literally an inside function here, 2x minus 3, so I'm going to let that be g. And then I have to think about what would be left. Well, I have the absolute value bars on the outside. So g of x would be the 2x minus 3 on the inside. And then the outside function's absolute value, but it has to have an input, so it's absolute value of x. So if I were to compose this, we would take our 2x minus 3, plug it in for the x, we'd have exactly this function that we've called h of x. So decomposition is just about being able to see and recognize that you have an inside and an outside function, which is, say, very important in classes such as calculus. And now we're going to look at evaluating compositions of functions numerically. We can do this at individual points for using either graphs or tables to find the values. We can do this numerically. So I could have written this with the circle notation as g circle f parentheses 0, but I've written it as the composition of functions there in parentheses notation, function notation, g of f of 0, which tells me what to do. I need to do f of 0 first on the inside. Okay? So you always work from the inside out when you have parentheses. So the first thing we need to do is find f of 0. To do that, I would go to x equals 0, visualize this vertical line to find where I hit the graph, and it would be there where the y value is 0. So for f of 0 is 0. So literally f of 0 is equal to 0. I can substitute that into my problem here. G of f of 0 would be g of 0, since f of 0 is 0. That leaves me with the task of finding g of 0. Now, don't get confused that this 0 that I have here was a y value, but now it's an x value. You kind of start over here. First thing I do is find f of 0, do the substitution. Then it's kind of like a new problem. I need to find g of 0. Okay? So when the input is 0, when x equals 0, g is negative 2. I find the point on the graph for g where x equals 0 and the y value is negative 2. Which would be my final solution. G of f of 0 is the same thing as g of 0, since f of 0 is 0, and that's equal to negative 2. Okay, second example, if we wanted to do f of g of 4, we would, on the inside, find g of 4 first. So we'd go to x equals 4, find our point on the g graph, and look and see that the y value is negative 4. So g of 4 is negative 4. We substitute that in. F of g of 4 then would be f of negative 4, and then again we think of it as kind of a brand new problem. We want to find f of negative 4. So at negative 4, the y value for f is 4. So f of g of 4 is equal to f of negative 4, which is 4. Okay, we can do the same thing with tables. Here I have the 3 columns where we have the x's, and then these would be the values of f of 1, f of 2, f of 3, f of 4, f of 5, f of 6, and g of 1, 2, 3, 4, 5, 6. So we can evaluate the functions with the table. And as long as we don't get thrown out of the range of our x values here, we can evaluate these with the table. So if we wanted to do f of g of 1, we would start by finding g of 1. And g of 1, we look to x equals 1, the g value is 2. So we substitute that in, g of 1 is 2, and then, again, new problem, let's find f of 2 to have our final solution. So when x is 2, f of 2 is 3. So when we work our way through both functions, f of g of 1 is equal to 3. Okay? So I got 3 more examples. If we look at f of g of 2, the first thing I would do is find g of 2. So when x equals 2, g is 3. So we replace g of 2 with 3, and we need f of 3. And when our input is 3, f is 4. So f of g of 2 winds up being 4. G of f of 3. First thing we do is find f of 3. F of 3 is 4, as we just said on the previous problem. So we replace that. We get g of 4. G of 4 is 1. When the input is 4, g's output is 1. And then finally, g of f of 4 is 1. When x equals 4, the y value for f is 1. So we substitute that in and find g of 1. And when you evaluate a function, even though it was a previous y value, again, it's now an x value. G of 1 means go to x equals 1, g of 1 is 2. And there we go. We've done some composition of functions. Then the last thing that I want to look at in the video here is what happens when you do composition with inverse functions. What happens is they wind up canceling each other out, as we're going to see here, in both directions. So I said let's let f of x be 2x minus 1, a nice linear function. We're going to find its inverse, so we'll review that real quickly. And we're going to call it g of x so that we don't have to worry about the inverse function notation. But then we're going to do the 2 compositions, f of g and g of f, and see what happens when you do that with inverses. So to find an inverse, we take our function and we take it out of function notation. So we've got y equals 2x minus 1. And we're going to reverse the role of x and y. So I like to solve for x first. Okay. So I add 1 to both sides, divide by 2. There's essentially my inverse function, but we also swap the labels. I'm going to also flip it across the equal sign there. So we've got x equals y plus 1 over 2. And then when we swap x and y, we got our inverse function, y equals x plus 1 over 2. We swap the labels because we want the input to always be called x. So we've got our 2 functions here, 2x minus 1, f is 2x minus 1, and g is x plus 1 over 2, which, if I did everything correctly, is the inverse of f. And we'll see that it is when we do composition because of what happens. So if we do f of g, we would take f's formula, 2x minus 1, take the variable out, and plug in g's entire formula, x plus 1 over 2, and then look at what happens. You're multiplying. You can think of this as 2 over 1 if it helps. So we've got a 2 on top, 2 on the bottom. They're going to cancel. And we're left with x plus 1 minus 1, which, when we drop those parentheses, is just x. And in the other direction, if we do g of f, we start with x plus 1 over 2, g's formula. We remove the variable. We plug in f's formula, 2x minus 1. And then in a slightly different order, it's all going to break down here. You get 2x minus 1 plus 1 on top. Once we drop the parentheses that I really just used to show the input operation, you're going to have 2x left on top divided by 2, which is x. So that's a property for inverse functions. It's a helpful way to check. If you do composition of a function with its inverse in either direction, you just get x.